So let's talk a bit more about MIPS and assembly language, and about how Mars places things into memory. So this is going to help us understand some of the more fundamental instructions and how they're used, with a big emphasis on the load word and the store word instructions, two instructions that are used to either put things into our .data segment or to remove things from, or at least to get a copy of things that are in the data segment. So if we're actually looking to put things or store things into the data segment, that's going to be a store word. If we're looking to load things or pull it out, it's going to be a load word. So this is going to help us kind of visualize what goes on with those two fundamental MIPS instructions. Throughout the book we'll talk, or throughout this lecture and in the book, the author talks about design principles and how they can make design either more complex or simpler, and what the compromises are. So there are some basic principles that are used. We've talked a little bit about registers. I'll bring that up. The MIPS memory model looks at memory as just many bytes, an array of bytes. So just like an array that's indexed 0, 1, 2, 3, 4, 5, 6, 7, 8, and so forth, these individual bytes are going to be addressed, and I'll use on occasion array notation to indicate a particular byte. And if I want the next byte, so that gives us a simple model for thinking about memory. And then within these addresses, so you can think of the index being an address. So just like an index in memory would be used to extract or look at an element, we can think of addresses being indices into arrays. We'll also talk about Indianness. You'll see that in a little bit. The idea of Indianness means that given you have something like this, CAFE, cafe beef, and each one of these hex values is 4 bits, so 2 of these is actually 8 bits, 8 bits, 8 bits, and 8 bits, and each one of those just really then is a byte. So we actually, for a typical value, a word value, so-called word value in MIPS, it's going to have 32 bits, but how would that be stored in memory? Since our memory works with bytes, we have a couple of choices. We can place it in here, such as EF, BE, FE, and CA. Right? Notice that I went from, let's do this. Notice that as I put those bytes into memory, I proceeded in this direction from the little or the least significant bit upward. Right? But there are other memory models that will go the other direction. It'll use a CA, FE, BE, EF. So which one of these is better? Is it going to be starting from the little end, or is it going to be starting from the big end first when it comes to storing these elements in memory? Where do you start first? So in this first example, we started from the little end and worked our way upwards. So that would be, that's commonly how, well, that is how Mars, our emulator, shows this. MIPS can actually be set up to work in either direction, but everything that we see in this class will be little end versus big end. So you'll see more about that a little bit later. And so there, you'll see that, in fact, that there are architectures that use both, or there are different architectures, and architectures could use, depending on the architecture, they could use different models. we'll get a chance eventually to talk about the green card, our reference sheet for MIPS, and more about memory layout. So these basic design principles are going to be more helpful as they come up in context. But the basic idea is keep it simple, and it makes the design simple, and it also allows sometimes for some regularity and speed advantages. So we're going to keep our registers always in the same place, and it simplifies the hardware design. You'll see what I mean by that as we start to lay out 32-bit instructions, and our fields are going to, which register is going to sit within which box is going to be consistent. In a 32 box, we're always going to know, given a particular register, where to look for information here, like where will these elements be stored in a 32-bit word. So there's going to be some consistency there that makes the design process easier. And also, there are some other advantages to the MIPS design versus using a more complicated design. What was considered once upon a time a bit more complicated, CISC, complex instruction set, versus RISC, reduced instruction set. And if you do the design well, you're going to have, it's going to take some compromise, but there are some advantages. And the things, we can't, since we have to represent every instruction with a 32-bit word, we're limited as to how many instructions we can represent, and we want enough. We want to make sure we have enough instructions so that we can do what we want to do, but we don't want to add so many instructions that the hardware gets too complicated. So the things that we do most commonly, such as maybe needing an immediate value in our instruction, right? We're going to see that instead of a regular add, there will be times when we need to do a different type of add, one that doesn't just work with registers, such as what we would see here, but one that works with registers and is also forgiving enough or flexible enough to allow us to put in an immediate value, meaning kind of a constant. It's immediately available and it's part of the instruction. And finally, we've looked at this by building a simple register in the previous lecture, and we changed this C, which think about it as either a clock, or sometimes it's used for control, or as enabling us to write the register outputs with the data bit. So when this D is a 1, we want to see that D, that data, be written to memory and show up here, and that won't happen until reg write, which sits at 0, goes to 1. So usually we'll just kind of send a pulse up and then have it hold, and that will send this output into a 1. Subsequent changes to our data, making it a 0, won't change this until the next pulse, the upward going pulse. And then once we get that 0 that's placed at this data input, on that next pulse, it will be written to the output. So that was a register that we looked at, and we can, if you want to see actual registers, you could take a look online and look at the 7400 series. Logisim is a powerful tool. There is a Tetris implementation of Tetris, the game itself, that we could actually look at. So if you download Logisim, a Logisim circuit file, you'll be able to look and see how you can use that to implement a couple of games. Tetris, I think, and Snake are the two that are shown there. Just like memory, registers are modeled as a one-dimensional array. So with registers, we have 32-bit registers, but we also happen to have 32 of them. Which one of those registers we select is going to be based on an index. So we're going to use this memory model similar to arrays, and we're going to use that to access various registers. So the values here for registers will just go up to up to something that allows us to get 32 different registers. And if we think about this, we need some number of bits to represent this index. And since this index is going to be a value from 0 to 31, if I only had 2 bits, the largest number I could represent with those 2 bits would be a 3. That is the largest number, so I could represent values 0 through 3 using only 2 bits. If I have 3 bits, I could represent values going from 0 to 2 to the 3 minus 1, so that's values 0 through 7. 4 bits gives me values 0 through 15, so I get 16 values. So I need 4 bits to represent 16 values, so 4 bits works out beautifully for hexadecimal. Now, since I have 32, if I go 1, 2, 3, 4, 5 bits, I'm able to represent values 0 through 31, or 32 different bits. So we need a 5-bit value to serve as this index. And we're going to, whatever that value is going to help us pull out information from these registers. So each one of these registers will contain 32-bit data, and then to access them I will have to set my index to one of those values that range from 0 to 31, so this index requires 5 bits. So it's a little bit confusing. 32 registers, each one of them will have 32 bits of information. And we've talked just a bit about memory. Memory is also going to be modeled as a one-dimensional array. So given that memory can be thought of as being analogous to an array, there is, let's go ahead and put our pen on here, there are areas that are set aside for different functions, essentially. So in this case, you're showing a stack, a certain area of memory reserved. We also reserve for a very specific function, but we also have an area of memory called a heap. We have the data segment and the text segment. The data segment we've seen when working with Mars using the dot data directive, the text segment. So our code, notice that over here on the left, we start from the very bottom at 0. We go up to 004 with 5 zeros afterwards, and it keeps increasing in value. 1, 2, 3, 4. And until finally we get up to the near the very top. So memory is increasing in this direction as we go upward. Data will typically be in this location here. Text segments will start at a lower area of memory. Low-level functions and kernel and operating system critical areas are typically reserved for addresses down in this space. Again, the stack here is used for typically function calls. and it grows downward. It's a temporary area. Typically a function might call and then call another function and call another function, and then it finishes its task and it comes back out of that. So this grows and shrinks, grows and shrinks. And with the heap, every time you use, in Java it would be a new, or in C it would be a malloc. And so this grows and then it shrinks whenever you free up the space. So whatever pointer was used to store the address of this memory that was allocated, you should also free it up. We've kind of had that discussion in another part of this class. So memory is reserved into these components. It's data, text, so text, data, heap, and stack, and then some lower level key components are down there. Alright, so you may see something that looks a little bit different when it comes to Mars. Let's see if I can write on this. So when it comes to Mars, you're actually going to see in our emulator an address of a 1001 with zeros following. And in order to use, or when this space would be used, is when we have an additional file to store our code. So typically you might have your main in one file, and let's say you declare that this here, external MySpace, is a directive that allows us to put together these separate object files, and then to be able to allow this other bit of code here to access that area of memory. So we won't see this in this course. I don't think we've had too many opportunities or need to work with separate files. But if you were working with two files, you would see this address space change. But for us, we're just going to typically see this because we'll just have the one file here that we work with, one file containing the source code. So what have we seen so far? We were introduced at a high level to the idea that memory is going to be modeled with this array model, with the indices being each index representing a particular byte. We've also seen this idea of storing things and storing bytes into memory using either the little n or the big end of a word, and I'm calling this cafe beef my 32-bit word. And we can decide to put this into memory using the little n first, or your assembler may use not little n first, but instead use big N first, and that's a different model. So we talked about that. We also did a quick review of what a latch is and how that can be used to store a single bit of information. This link here could be accessed. You could access that to see how you can combine a single 1-bit register, which is what we're looking at here. You can use this link regforward.cir, and you with this PowerPoint, then you can go in and see how a 4-bit register is implemented. Right now we're just looking at a single 1-bit register. The 1-bit being this Q bit here is the bit, the value that we wish to save. We put it into data and it's saved in the output. So Q is conventionally used for an output, and then to write it into that location we use regwrite. So Registers are also frequently modeled as a one-dimensional array. As I said before, there are 32 of them, but that 1 bit that I showed you is a simple register. 32-bit registers are what we're going to use in this class, and we have 32 of them. We need 5 bits to access each one of those 32 registers. So 5 bits give us access, and we think about it as an array. That index value is going to be anywhere, RD or RS or RT, but that index value can be anywhere from 0 to 31. It will take 5 bits. You'll see how that comes into play when we look at how instructions are, how they reside in memory, how they're stored typically as a single number, a single value. And then finally, I think, the next thing we looked at was how we have various storage locations, tags, identifiers for different areas of memory. The data segment, text segment, stack segment, and heap are the biggies. And one thing that's important here to remember is that as we use the stack, as it grows downward in size. As you run code, run functions, every time you use more memory, this is growing downward in size, versus heaps that grow upward in size as you use them. So we'll see how that comes into play. And then a little bit about Mars, how it actually stores. For most every project that we're going to use, you're going to see the 1001 with 4 zeros as the address for your variables. It will start there. And then next we'll talk a little bit about how we'll look more directly at endianness, big N, little n, and what that looks like actually in Mars. So I'll save that for the next discussion. Big N, little n, so-called endianness.